Welcome back to DeepVisus, where vision meets depth. I'm your host, and in today's episode, we're embarking on a truly foundational journey exploring nothing less than the very blueprint of the brain, how its intricate structure self-organizes during development, and how fundamental biological processes contribute to its remarkable functional architecture. Our guide for this profound exploration is the very last chapter of our current series, Chapter 18, titled Neural Field Dynamics and the Evolution of the Cerebral Cortex, authored by James J. Wright and Paul D. Bourke from the insightful book, Neural Fields Theory and Applications, published in 2014. This chapter offers a sweeping perspective linking the evolution of species with the prenatal development of an individual's brain. So, for today's central question, how does the brain's intricate structure, particularly the cerebral cortex, self-organize during its earliest developmental stages, and how do fundamental biological processes, even seemingly destructive ones, contribute to its remarkable functional architecture, preparing it for a lifetime of learning? To begin to answer this, let's revisit a concept we've touched upon before: neural fields. As a reminder, these are mathematical models that describe the large-scale, continuous activity patterns of vast populations of neurons rather than focusing on individual cell firing. Think of them as dynamic landscapes of electrical activity across brain regions. Now, a critical and somewhat surprising player in this developmental story is synchronous oscillation. This refers to the phenomenon where large groups of neurons fire together in rhythmic, synchronized patterns. What's fascinating is that these synchronous oscillations occur very early in embryonic development, even before sensory experiences begin to shape the brain. Here's where the seemingly paradoxical part comes in. This synchronous activity is intimately linked to apoptosis, which is programmed cell death. Apoptosis is a natural, essential process where cells self-destruct. The authors propose that synchronous firing actually protects neurons from apoptosis. Imagine a competition for vital metabolic resources. Cell groups that are interlinked and fire in maximum synchrony are more efficient at securing these resources, thus surviving, while others, less synchronized, perish. This isn't just random survival, it's a selective process. This selective survival, driven by synchronous activity, leads to the formation of networks with what are called ultra-small world characteristics. This is a highly efficient network structure where, despite having many connections, the average path length between any two neurons is remarkably short. It's like having a vast city where you can get from any point to any other point in just a few steps. This efficiency minimizes metabolic cost and maximizes information transfer, which is crucial for a developing brain. The chapter then applies these principles to the visual cortex, specifically the primary visual cortex, or V1. This is the first cortical area to process visual information. V1 is well studied, making it an ideal candidate for testing these developmental theories. One of the key features of V1 is its orientation preference, or OP, where neurons respond best to lines or edges of a specific orientation, like vertical or horizontal. These preferences are organized into intricate maps across the cortical surface. Another puzzle in V1 is the superficial patch system. This is a network of relatively long-range, patchy connections found in the outer layers of the cortex. These connections link areas that share similar functional properties, like the same orientation preference, even if they are physically distant. The authors propose that the competitive survival process, driven by synchronous oscillations, naturally leads to the emergence of this patchy system and the hexagonal organization often observed in OP maps. To explain how visual information is topologically mapped onto the cortex, the chapter uses a clever analogy: the Mobius strip. This is a fascinating mathematical surface that has only one side and one boundary. The model suggests that the brain projects signals from the surrounding cortex onto each macrocolumn, a functional unit within V1, in a way that's analogous to projecting a Euclidean plane onto a Mobius strip. This allows for a continuous representation of orientation despite the seemingly complex organization. So, how does all this prenatal self-organization become functional after birth? This is where Hebbian learning comes into play. You might know its famous adage, neurons that fire together wire together. This principle describes how synaptic connections are strengthened when neurons are active simultaneously. After eye-opening, direct visual inputs through Hebbian learning refine and overwrite these earlier antenatal configurations. The brain's initial prevision blueprint is then etched with the details of actual visual experience, leading to the development of mature, selective tuning to specific visual features like moving lines of different velocities and orientations. In conclusion, Chapter 18 provides a truly elegant and comprehensive answer to our central question. It posits that the cerebral cortex's intricate functional architecture self-organizes through a synergistic interplay of synchronous neural field oscillations and the selective pruning of neurons via apoptosis, leading to metabolically efficient, ultra-small-world networks. This prenatal blueprint, including the organization of orientation preference and patchy connections, is then refined and specialized by Hebbian learning once sensory experience begins. This unified model not only explains various experimental observations but also suggests a general principle for the evolution of increasingly complex sensory motor sequences both across species and within an individual's lifetime. It paints a picture of the brain as a self-organizing system, constantly optimizing its structure for efficient information processing. This exploration into the brain's developmental blueprint is just one more incredible facet of the brain's complexity. Join us next time on DeepVisus as we continue to explore the fascinating world of brain, mind, and intelligence. Stay tuned.